So I'm Spencer Dansereau. I'm a PhD student here at the University of Colorado Boulder, second year-ish. Started working with David Marshall in 2018, but just finished my second year here at the PhD program. This will be on novel ceramic composite fabrication, which is NANO-LAYER technique where we're putting thin layers down, and I'll get into why we're doing that and the process in which we do that. Quick introduction just to CMCs, not going to delve too much into it as many people have touched upon the uses and what are polymer drive ceramics, but as I'm part of the aerospace department here, one of our major motivations for this is hypersonics as well as rocket engines and as well as propulsion systems like we heard from GE, as well as Pratt & Whitney engines and Rolls-Royce engines, things like that. Also, additionally, nuclear is a focus point for many applications of these CMCs. So diving right into our NANO-LAYER system that we're working on, we need to look at first the polymer infiltration process, the PIP process. And when we do a first round of PIP infiltration, we get lots of cracks. As we heard from Starfire, you can go up to 6-7 recycle processes with SMP10, for instance, and you have lots of different cracks in that. Now, through that process, it can be kind of difficult to fill all of those cracks. So the process we're looking at right now is laying down a thickness that is below the point of cracking. For instance, if you put on a really thick layer of paint or mud on the ground, it's going to crack as it dries. However, if it's thin enough, you can actually get it to dry and shrink without cracking. That's the process that was initially investigated by Zoli here at the University of Colorado in 2016. And you can see this is an image from that paper looking at basically diluting what we're using, either toluene. They were using Saracet and toluene. We're looking at SMP10 in hexane as the dilution agent, solvent rather. And basically we're putting on really thin layers using 120 microliters drop onto a surface, and that wets out evenly across all fibers. And essentially we're looking at getting a 100 nanometer to 500 nanometer layer of silicon carbide per layer as we build up the matrix. This allows for the benefit of a highly controlled porosity. For the 500 nanometer layer, we can do it in a fairly quick cycle that allows for a buildup of a full matrix or around, say, a woven pattern that has particulates in it, and we can build up the matrix in that manner. For the slower process, say reduced to 0.1% of SMP10 to hexane, we can build up slower, so we can allow for controlled porosity, which in turn controlled permeability for transpiration cooling applications. Porosity control. So one of the things with SMP10, when you re-infiltrate through the PIP process, you fill in voids differently, depending on what the void shape is. And shape like this, something like a balloon shape where you have, I think you guys can maybe see my mouse here, this narrow section here, it'll build evenly across the entire inside, and then it will end up closing off this piece here before it actually fills the whole void. So you end up with voids still throughout the whole matrix. Of course, with a CVD process, they're very energy intensive and very long, but you don't have this issue. However, we're looking to a pre-ceramic polymer PIP process that allows for a fully dense matrix buildup as well as this porosity. So again, that's just what we can see here. It's blocking it. The favorable surface tension and polymer wetting technique characteristics of a highly diluted SMP10 allow it to actually fill this back void first. You actually get it pulling off of here because of the convexity and concavity of the surfaces here. It'll actually pull that polymer back into the back and fill in the whole void as we move forward, and thus allowing new matrix to fill in everything. So our specific aims here, we're looking to optimize a robotic system that allows for the deposition and infiltration of polymer concentration. We're looking at polymer concentration, type of solvent, and whether we should add silicon carbide microparticles, which is kind of where we're at right now, and look at how that can modulate our porosity and thus permeability. Here is just a basic schematic of the current robotic system that's being used in the laboratory. First, a matrix material, right now it's between 0.1% and 1% SMP10 to hexane is deposited. It's then moved automatically to a 350-degree cross-linking furnace, then onto a 900-degree C furnace for full cross-linking, and then onto a cooling chamber, and it returns back here. It's about a 1.5 minute process because it's such a thin layer. At 100 nanometers, it's fully pyrolyzed in a 1.5 minutes. And here's just a SolidWorks model, kind of get more a physical representation of what's going on here. We have cameras set up so we can actually look at it as it's going through each cycle, an automated deposition system as well as cooling systems. We're using the high nickel type S fiber for the preform, the Starfire SMP10 as the matrix precursor. Here is just some initial images of the 500 nanometer setup, so 1% SMP10 with hexane. Total number of cycles on this one was 10. And then here we have at 15, we can see we're actually building up a pretty uniform dense matrix on here. And then here at 30 cycles, we have a somewhat fully dense microcomposite after those 30 cycles. So if we analyze a little further, we can see, again, that's 500 nanometers per cycle. However, if we look across the length of each fiber, we look to see, how good is this actually moving across the whole fiber? So took images roughly 700 microns apart and drop size of 120 milliliters, and saw a thickness variation of 200, actually that should be 200 nanometers, sorry, 200 nanometers per 700 microns at 5 cycles. And then, like I was saying earlier, we want to actually reduce down that thickness that we actually deposit so that we can really, really accurately control the porosity, thus permeability of the system. So here are some SEM micrographs of the 0.1% SMP10 with hexane with a reduced layer thickness to 100 nanometers per cycle. So where we're at currently is measuring permeability and moving to including different actual particles into the matrix, both circular silicon carbide powders of different sizes, 4 micron up to 10 micron, as well as potentially adding in carbon nanotubes into the precursor to allow for modulation of accurate permeability. And applications for these permeable systems, here's a paper from 2014 that is looking exactly what we're looking to do. Is hypersonic leading edges of vehicles need to be very, very sharp to allow for control surfaces without ablation, because as you ablate and it gets not as sharp, you lose more of that control of the fluid flow over the surface, so you need to keep it nice and sharp. However, the heat flux at those locations, the radius of curvature can be less than 3 millimeters, which is really, really small. The heat flux is wildly high, so you have to actually actively cool the surface because the operational temperature of silicon carbide composites is not adequate. So Capri asked me to give a quick introduction into my company and some of the projects that use CMCs that we're working on. So we're drawing from other advanced propulsion systems such as the Sabre technologies from reaction engines, as well as Vasimir from Ad Astra of electrodeless electric propulsion to work on an initial prototype for a high mass flow rate all-electric supersonic propulsion system that is enabled by ceramic matrix composites because it's operating at very high temperatures, and we use radio frequency excitation and electromagnetic fields to accelerate high mass flow rates of air plasma through the system. Additionally, some work on CO2 derived carbon fibers from carbon nanotubes as additions into PDCs, but also fiber spinning, and then soft robotic applications as well. So just a quick overview of the projects that working on with the NANO-LAYER, and I'm happy to take any questions.